Okay, thanks for the introduction. So, good afternoon, everyone, and welcome to this talk. So, I'll talk about modular construction of live Byzantine consensus protocols. So, I chatted to Peter during the break, and he said, well, we should have every school that we have. We always have a talk about state machine replication or Byzantine stuff of some sort. Okay, so that's so my talk is one of the representatives of this idea. All right, so. So the organizers asked me to give them the title sometime in advance. So I thought, okay, so we have some papers in this area. So I thought, okay, so how about I talk about it? And then when I started preparing the talk, I actually realized that a lot of techniques and mechanisms underlying this subject of liveness in Byzantine consensus can actually be derived and discussed just as well in the benign setting where we only have crash failures. It does not mean that I'm not going to talk about Byzantine things, right? But I'll start gradually, so I'll start from kind of more familiar and more comfortable, if you want, a crash failure model. And then we will see some principles on the examples of some algorithms. And then from there, hopefully, it's going to be very natural to proceed to the more challenging Byzantine setting. Okay, so I'm throwing in the air a lot of words that maybe not everyone familiar with or equally familiar with, like Byzantine, live, maybe even consensus, I don't know. Anyone who knows about consensus? Everyone? Okay, yeah, okay. So my task is easy, okay, so I just go. Right, okay. So, so here's the overview. So even though you guys are very good, is the font okay? Can you see it? Yeah, okay. Okay. Looks kind of small to me from here. Okay. Anyway, so I will still talk about consensus and state machine replication just to introduce and motivate the problem. Then I will talk about this liveness problem, that something that we think has been missing until recently in the framework that kind of the programming framework that can be used for building consensus algorithms, for partial synchrony in particular. So then, so that's the motivational part. So then we'll start doing some more technical stuff. So as a warm-up, we talk about crash fault-tolerant consensus in synchronous round model. So that would motivate the framework that I'm going to talk about, which is round-based or then later on a view-based. Okay, and then I will show you a simple round synchronizer for a crash fault-tolerant setting. So round synchronizer essentially is a module that's going to create this illusion of rounds that we all like, right? Using some timeliness assumptions available in the system. Okay, and what is interesting is that, as we will see, although here we are still in the asynchronous model, right? The techniques and principles are already transferable to less synchronous model, to partial synchronous model, etc. Right? And the same goes about failure. So this first synchronizer is going to be completely in benign failure model, but the basic principles actually apply in the Byzantine failure model. It's quite easy to extend it for Byzantine consensus. Okay, so yeah, so then so here we finish with the crash failure model, and we kind of going to this realm of partial synchrony. So in partial synchrony, we replace rounds with views because we want to separate safety from liveness, right? So we don't want safety to depend on rounds because round can be asynchronous before system stabilizes, right? So we only want the liveness depend on rounds. So that warrants some change in terminology. So instead of talking about rounds, we're talking about views. Then I'll talk about partial synchronous crash fault-tolerant consensus in the view-based system. So this is more or less similar to Paxos protocol, but it needs some adjustments so that to make it work in this view-based model. But if you're familiar with Paxos, that of course help, but I'm not going to assume any prior knowledge. So then we talk about crash fault-tolerant synchronizer for partial synchrony, which is going to be very similar to the one for normal synchrony. Then we change the gears. Finally, we get to Byzantine fault tolerance, and I discuss Byzantine fault tolerance synchronizer. And then the last thing we do is that we see how we can use a synchronizer to build a Byzantine fault-tolerant consensus and state machine replication. Okay, so my goal today that after the lecture, you will have a very good idea how to construct a Byzantine fault-tolerant or crash fault-tolerant consensus, which is provably live and safe, using a principled framework of synchronizers. Okay, so that's my goal. All right, so any questions, please just don't hesitate to ask. Just raise the hand or just go ahead and ask. Okay, so that's fine. So I really wanted to be interactive. So if you are not asking questions, I will be asking questions. So I will be asking questions anyway. Okay. So be prepared to answer questions. Okay. So what is consensus? So setup is very simple. We have a network of n nodes or processes. The interface is propose a value and then decide a value. Okay. So I'm not necessarily going to talk about this proposed part explicitly. So in our discussion, we kind of, in many places, we will assume that the value is just, every process just has something to propose or already has a value, right? So I won't be explicit about this proposed interface just to keep things simple. But if you want to see how that could be done, if we actually have this proposed interface and we have like repeated consensus or multi-shot consensus thing, you can look it up in the papers. Okay. So the properties of consensus are agreement. All decision values must be the same. Okay. Validity, every decision value must have been proposed. And termination, all processes eventually decide. Okay. So of course, what makes consensus interesting is that processes may fail, right? So when I say all processes decide, of course, I need to qualify that only process that does not fail decide, right? So I need to say something like, should not rely on technology too much. So here perhaps I should say something like all correct. All correct eventually decide, right? But I don't want to complicate because the notion of correctness depends on the specific failure model that you're using. So we will keep it for later. Okay, and of course consensus has lots of applications. So this is why everyone these days interested in consensus. And I ask a group of students, if you've heard about consensus, everyone did, right? Because blockchains, of course, drive a lot of interest. But consensus has been used for ages for many other settings, primarily in data replication. So of course, blockchain and data replication, they're not independent, right? And transaction commit, right? So that if you recall Alexei's talk from yesterday, say to guarantee serializability or strict serializability or even snapshot isolation in a distributed system where the database is partitioned, you need to use consensus, right? So consensus is super useful. And the usefulness of consensus can be represented as this concept of state machine replication. Okay, so what is state machine replication? Replicas are identical deterministic state machines. So you can see here that that's indeed the case, right? So they are all blue. They have the same word written here. They have the same two fans and everything here, right? So they look pretty identical to me, right? And then, so once we have identical deterministic state machines, then if we have some magic that ensures that every command or every transaction is processed in the same order everywhere, right? Then they all in consistent state all the time, right? So this is state machine replication. And you implement state machine replication using consensus, of course, right? So one way to see it is that you use consensus to decide which command should occupy a specific slot number, right? So you can imagine, like, there are some slots here, right? Not all of them occupied, right? And then you essentially run consensus per slot like this, right? And then you reach a decision. For example, B must go in slot 2, and this is what's going to happen, right? So when this guy here gets B, then B is going to be here as well, right? Any questions so far? All right. Okay. So consensus is equivalent to state machine replication, right? So that's important observation. So yes, so from theoretical perspective, I'm a bit loose here. So I say state machine replication, but I kind of didn't define state machine replication as an abstract problem. But there are ways to do this. So there is a primitive called atomic broadcast, for example, right? So atomic broadcast is something that ensures this order, this total order here, right? So that's atomic broadcast, right? So strictly speaking, I should have said consensus equivalent to atomic broadcast, but just keep in mind to keep things simple. Okay, so we talk about state machine replication. Okay, so by the way, so I just showed to you how implement state machine replication using consensus. How can I show the opposite direction? How can I do consensus using state machine replication? Yeah? So in consensus, I need to decide on the same value everywhere. So how do I do this?
You try to write your value in the log and then replicate it and see which value was written as the next in the log.
Yeah. Okay. So I can just essentially, if I have these logs here, right? Okay. So that's a magic of state. So someone gave me this black box state machine replication and it somehow by some magic produces these logs. So what I can do is just I pick the first and then I every value proposed I kind of give them to state machine replication and tell the state machine replication decide which slot it goes, right? So then some of the proposed values will go in the first slot, right? And they can just as well decide this value, right? It's going to be the same everywhere. Okay, so state machine replication and consensus are two equivalent things. Okay, so So next thing I wanted to discuss solvability of consensus, and then I wrote this boring slide here, which has a lot of words. But then I discovered this nice infographics by Itai Abraham, right? So actually, if you want to learn things about consensus, arbitrary replication, Byzantine case, non-Byzantine case, everything, it's I would really recommend to read his blog, because it has a nice combination of more classical things, more like foundational things, and also more novel things, more kind of cutting edge of technology and research things. And there are a lot of guest bloggers that write about their new exciting research. So it's a really nice blog. It's called Decentralized Thoughts. Okay, so here's the infographics about consensus solvability in various failure models. Okay, so crash failures basically means that process crashes and then that stops taking any steps forever. Omission failures, you can imagine that every process has kind of a bubble around it, and then this bubble can drop some messages, right? So the kind of inside the bubble, the process behaves correctly, meaning according to the protocol, but around the bubble, within the bubble, there is some logic, if you want, that may drop some messages, either incoming or outgoing. Okay, so this is the omission model. So omission model is, in terms of the adversarial strength, it is stricter than the crash model. Okay, so it might be a bit confusing because actually omission model allows for more failures, right? So the failure behavior that allowed by omission model include crash model, because the bubble can just drop all messages, and then this process is essentially crashed, right? Okay, but it can do more things as well, right? So it can selectively drop some messages. And then Byzantine model is the least restrictive one, so everything is allowed, right? So in Byzantine model, you can do omissions, you can do crashes, and plus you can do everything else, right? So essentially, I can just execute completely different protocol. I don't have to, forward the messages that I'm supposed to forward, sign the messages in the right way. I can try to collude with other processes to impersonate for some other process and whatnot. Okay, so everything is allowed. Okay, so so the right way to read this diagram, so it's a bit compressed, but you can say, okay. So for example, if you look at synchrony, then consensus is possible for any number of failures less than n if it is crash. Okay, and so there is also a bound on performance that said that there are some executions of any protocol that solves synchronous consensus that would have f+1 rounds. Then in omission, if f is greater than n/2, okay, greater than half, then it is impossible to solve even synchronous consensus, right? But then you may ask, okay, so where is so what is possible, right? So to know what is possible, you can look at the next slot here, right? Because Byzantine model is less restrictive than omission. Therefore, if I can solve it in Byzantine model, right, with these many processes, then I can also use the same protocol to solve consensus with omissions. Okay. Right. So okay. So about this bound here. So in Byzantine with Byzantine failures synchrony. So actually, there is an assumption of availability of message authentication. So this is what it means here when it says PKI, right? So public key infrastructure, so I can sign messages in this model. And that prevents process impersonation. So the reason this algorithm would work with the mission is that in the mission, processes don't impersonate, so I don't really need to sign anything. So protocol would just work as is. So if you don't have PKI, then there is a lower bound. So especially one famous lower bound by Fisher, Lynch, and Merritt that had some topological construction as a precursor of work on topology that Sergio discussed that shows that even in synchrony, you need you can't tolerate more than 1/3 of failures. Okay. So partial synchrony. So what is partial synchrony? So partial synchrony means that the system initially can be completely asynchronous, and then after some unknown point in time, it stabilizes. Okay, so it looks something like this. So this time is called global stabilization time, GST. Okay, so before GST, there are no any timeliness assumptions, and after GST, there are some timeliness assumptions. Okay, so we'll talk about it in more detail. I'll tell you exactly what are these timeliness assumptions and so forth. Okay, so this model. So if I want to compare this model to this model is practical one. Okay, so it was very successful in the industry, and particularly protocols that were developed for this model, such as Paxos, for example, gained wide adoption. Right, so people probably familiar with Raft, Zookeeper. Right, so they're all derivatives of the Paxos algorithm by Lamport. Right. So this is the most interesting model, let's say, from the practical perspective. So there are some bounds in this model. So you need at least majority correct to solve it with crash. Okay. Then with omission, so omission is stricter than crash. So if you have this impossibility for a crash, then it also applies for omission, obviously. And then you also have a Paxos algorithm that works for omission. Okay, therefore it works for crash as well. Okay, so now what happens with Byzantine failures? So it's possible with f less than n/3, so you can tolerate up to third faulty processes. Yeah. Okay, so omission, you can imagine. Okay, so I talked about bubble, right? There is a bubble around every process. Well, there is no physical bubble. This is how I explain it. Okay. Okay, so that means that everything inside the bubble, it's a process that executes the correct protocol, right? So it's not Byzantine model. So the process, they follow the protocol, and they can send messages, right? So we can send message, then this message arrives, this process receives message, right? So the bubble has a power to stop this. So for example, I send a message, but bubble stops this message. It is never been sent. Yeah, absolutely. Yeah. So a mission model does not put any restriction on the bubble of what can happen in the bubble. Does it make sense? Okay. Well, you don't have to describe a mission model with the bubble, but I find that this simplifies things for people. Right. Okay, so for partial synchrony, we have so we have algorithms that were originally developed in this paper by Dwork, Lynch, and Stockmar in '88, And there are algorithms for both authenticated model with PKI, and there are algorithms for a general Byzantine model. Okay, so they also have algorithm for omission and for crash, right? So if you read this paper, you will find that amazingly this paper actually solved all the problems in '88, right? But Paxos, so but the machinery that it used was not very simple to follow. So Paxos kind of took the ideas and condensed it in a very concise, accessible way. And this is how Paxos essentially become the golden standard of partial synchronous consensus, whereas the DLS protocols are normally just used for Byzantine consensus. Okay, so those are these two models, synchrony and partial synchrony. So we will be mostly talking about these two models. But so what happens with the synchrony? Of course, there is a famous FLP result that a deterministic consensus can't be solved in the synchronous model. Okay, but the world is not binary, so you can say that you can look into this vast area of randomized algorithms, and then you will discover that there are some nice solutions in this realm, right? So if you so depending on your trade-off, you can have a randomized algorithm which is quite efficient. So by the way, a question to you. So what can you give an example of a randomized consensus that essentially everyone is familiar with, maybe without realizing? What? Raft is not randomized. Say randomized that may, with some probability, violate agreement. With some low probability. Think about blockchain. Anyone? No? So a proof of work is a randomized consensus. Okay. So when it was invented, it was of course not presented as randomized consensus, but then people worked on it, and then they discovered that they proved some bounds, and they had a precise analysis of probability of forks and things like that, right? So there is a probability that Nakamoto consensus would generate a fork. Okay. So this is a consensus algorithm, but it has probabilistic safety guarantees. Right. Okay. So if you have, so there is the same information summarized here with some references to papers you can explore on your own. Okay. So now switching gears, so I want to talk about the liveness challenge. Okay. So what is the liveness challenge? So essentially, we want. As I said before, we want to consider this system, partial synchrony system. Okay, so partial synchrony system is the most practical one, right? The most popular, and essentially people in industry develop consensus state machine replication, assuming partial synchrony. Okay, and then. Well, it kind of, I won't tell you the entire story, but when we started looking at this, we realized that the history of people working on partial synchronous consensus is essentially history of evading the liveness problem. Okay, so everyone was very much focused how I can build a safe consensus algorithm. By the way, safety liveness, this is how is it okay? So what is the safety properties of consensus? So we had three properties: agreement, validity, termination. So which one of those are safety? Can you speak up? Agreement and validity are safety, and termination is liveness, right? So safety properties, they rule out anything bad happening in the execution, right? Okay, so once agreement is violated, then there is no way to fix it, okay? Once safety property is broken, that's it, game over, right? The liveness property are a complement of that, right? So I may not have agreement for very, very long time, but then I know that it is possible to extend my execution where agreement does occur, right? So there is termination. So this is the difference between safety and termination. Okay, so so if you look historically, what happened in this area, and I've been working in this area for quite a long time, so the people essentially said, okay, so the most important thing is safety. So let's just focus on that, and then ensure that agreement never violated. It's very decent objective to have, right? Because agreement is really important thing. So this is what we care about, right? So it's better not to have a fork in the blockchain than actually do something, right? So if there is no, nothing happens, new blocks are not added, that at least there is no fork, right? So it's a kind of mindset. So people said things like, okay, so we have this abstraction of failure detector. Failure detector completely abstract away time, right? So now I can just develop a safe algorithm, which is safe in complete asynchrony. And then for all the liveness part, I just ask failure detector to take care of. Okay, so that's approach that was very popular. But failure detectors have limitations, so they only been defined for crash failures, right? And it's very difficult to actually define what it means for failure detector to work in a Byzantine setting, because a process can deviate from its prescribed behavior, right? So this is essentially algorithm protocol dependent, application dependent. So how can we identify these deviations? It's not clear. It's not even possible to do this. So what happens in BFT world, in Byzantine fault-tolerant world? Okay, so one influential protocol that solved consensus in partial synchrony is PBFT, practical Byzantine fault tolerance. Had very detailed safety proof, but then essentially just 2 paragraphs arguing about liveness, and then if you try to read it carefully, you realize you don't understand how it works and why it works. And people actually tried to implement PBFT in VMware, and they discovered that what is written there is can't be just there are problems with that. They had to come up with all kinds of solutions and work around. So it was not simple. So liveness bugs have been discovered in production systems such as Tendermint, Casper. Okay, so some variants of PBFT. And the fundamental reason for that is that people, when they, when it comes to developing protocols, and so now we don't have this, we can't compartmentalize failures and synchrony in the module like a failure detector. So now I need to actually deal with everything related to liveness, like handling timeouts and things like that, directly in my code, right? And this is challenging, right? So you need to know when to wait for how much, and so on and so forth. So you essentially end up in this spaghetti code where everything is intertwined, and chances are it's not going to be correct. Okay, so some more examples from actual academic papers that so one famous one is Ziziva, which got best paper award in the top systems conference in 2007. Then after 10 years, this paper appears, and then essentially saying that there is a serious bug in the protocol. Okay, so then there was this survey by Toloniat and Gramoli, who discussed many different problems with the existing protocols, and with some examples. So you can see that out of 6, there are three of them have had liveness issues. Okay. So this is just to illustrate what happens if you don't have a good separation between safety and liveness. So this is the actual pseudocode of Tendermint from a paper by the people who actually developed the system. So if you zoom in, you have things like this. Okay. So there's some condition here: schedule, on timeout, pre-vote, be executed after timeout, pre-vote, something like this. Okay, so that's really cryptic, really difficult to understand what purpose this magical condition actually serve. Okay, so the same thing about here, and so on. Okay, and yeah, it's not surprising that problems were found with this algorithm. Okay, so another one? Anyone read this book? No? It's a great book, actually. I use it for my distributed systems class, but not the part which talks about Byzantine consensus, because it is broken. It is broken, and what is broken is liveness. Okay. I'm not going to discuss it in much detail, but you can, if you can read in our one of our papers, we actually describe what the problems are. Right. So now, okay. So this was the situation when we started looking at these liveness challenges, and we tried to understand. Okay, so what's going on, right? So our realization was that the problem is that the mechanisms that are needed for liveness, such as those that deal with timeliness in the system, are not separated from the mechanisms that deal with safety. Okay, so that's this is something that leads to all these bugs and difficulties, and makes this algorithm challenging to design. So we thought, okay, so we need to come up with some principled framework that would allow this separation. Okay. So, and we came up with this view-based framework, and then that indeed, hopefully, I will convince you by the end of my presentation that actually makes things much simpler. But before I start discussing the view-based framework, let's just take a step back and see what happened with some classical consensus algorithms. Because it turns out that there were solutions in the past. And if you look closely at the classical algorithms, you will find ways how you can deal with this problem. But of course, it can't be taken just as is. You need to do some adaptations. But there are some underlying techniques, some fundamental techniques that remain the same. Okay, so let's look at synchronous crash fault-tolerant consensus. So what is crash failure model? So this everyone knows about that. So n nodes, reliable point-to-point links, we're going to assume. There is some threshold of processes, F, that can experience crash failure. So a crash failure in the crash failure model means that the process stops executing forever and never comes back. Okay. So then there is this dichotomy: process that never fails is correct. And of course, we need, if you're talking about consensus, we need to modify termination condition to say that all correct processes eventually decide. Okay, so of course we can't ask faulty processes to do anything. So when people think about solving consensus with this model, they like to consider this what is known as basic round model. Okay, so what is basic round model? So computation is divided into series of rounds, consecutive integers 1 to 3. So in each round R, there is a send subround. So in send subround, each node sends messages to any subset of nodes. It can be empty, right? So some nodes may not send messages. It's allowed. Then there is a receive subround. Each node delivers some subset of messages that have been sent to it in the round. And then there is a computation subround that essentially makes some state transition based on the messages that received. Okay, so this state transition in particular may determine which messages are going to be sent in the next round. Okay. So there is one condition which is important, that all messages sent from correct nodes to correct nodes at every round are delivered at the same round. Okay, so this is what is called communication closed round, right? So you can't have rounds, you can't have messages somehow spilled over to the next round, for example. Okay, and we have this guarantee for all correct nodes, right? So faulty nodes, the messages sent by faulty nodes can be partially delivered by some process, not delivered by others. Okay, but they never overtake to the next round because of this condition that we also required to deliver a subset of messages that were sent. Okay. So this is a basic round model. Okay. Clean and simple. Okay, so now you have to develop an algorithm to solve consensus in this model. I'm gonna insist that someone tell me how to solve consensus with this model. It was the very first algorithm, the distributed algorithm that I have ever seen back in time. And it is simple. How we solve consensus in this model with rounds and crash failures. Let's be more specific. Okay. So here is the first round. Okay. Those are processes, and they have some initial values, say 1, 2, and 3. Okay. So the first round is the send round. So what we do in the send round? First sub round is the send of every round is send round. So we send some messages. So what am I gonna do? I send what? Send which value that I have. Okay. So we said that we assume that everyone has some value proposed. Okay. So everyone sends a value to everyone. Okay. Okay. Then, okay, so somewhere here that all messages have been delivered, right? That been sent. What shall I do? Can I terminate now? Here's the question. Can I just do everything in one round? Who thinks yes? Who thinks I can do everything in one round? What? Okay, let's let's see. Okay, so so there are many ways to do this. Okay, so this is probably the simplest way. So I have this state W, which initially every process just puts inside its initial value. Okay, so we're talking, say, about process PI with initial value VI, right? Then I have rounds. So you can see from here that I can't. Okay, so the way it looks like, I can't decide in one round. Okay, I need f+1 round. So so while I'm describing that, tell me why. Think about why I need actually f+1 rounds. Okay, so what I'm gonna do, I'm gonna send the W to all processes, right? Then I accumulate all the values that I have, all the sets W that I have received, and then I add them to my set W. Okay, and I continue doing so until I reach round f+1, and at round f+1 I can decide. Why can I decide at round f+1? Mm-hmm. F is the number of is the threshold on the number of failures, of crash failures. Okay. So why can I decide in f+1? Why can't I decide earlier?
If nodes like crashed, when you will get knowledge that for correct nodes you get data more than F. Right?
Sort of. Okay. So f+1 means that if you have just F failures, right? At most F failures means that if I ran for f+1 rounds, then I had one round in which no one has failed, right? So that's the key observation here. So I have this round in which no one has failed. So that's key to proving agreement. Okay. So in this round in which no one has failed, essentially all correct processes, all processes who were alive in this round, right? They just exchanged their W's, and they produced the union of all these W's, right? And then they end up with the same W. Okay. Just a second, and then I also have this technical condition, which basically says that new values can't appear out of the blue, right? So once I have this full set of identical values W, then okay, everyone is going to see this until the end of the protocol, and then it is of course safe to decide on some value in this, some deterministically chosen value in this set. Okay, so this is the idea of the proof. And validity determination in this case are trivial. Yeah.
How do you count failures over time?
I don't count failures over time. I count rounds.
Yeah, but I guess you're saying the equals no matter how much rounds you have. So you have
No, I need to have at least f+1. Otherwise, I don't have this guarantee that there is a failure-free round.
Yeah, I mean, but
Is it okay? Are you okay with this logic? That if I run for f+1 rounds, then there is a failure-free round.
no.
No? Okay.
I thought the agreement was that we aren't allowed to have more than F failures in a single round. But
No, you can have any. There is a global threshold F. You can have any a number of failures in every round, right? But you can't, in total, can't be more than f. So the worst case, what adversary can do, it can just fail one process in every round, and then it will be forcing me to run for f+1 rounds, right, to achieve a failure-free round. Okay, but if adversary actually crushed everyone who had to be crushed in the first round, then okay, in theory I could have decided in the next round. I just don't know that, right? That no. Okay, that's a very okay. Please remember this, because that's going to be important, okay? This is the crash failure model. Okay, so I hope everyone understands how it works and why it works. So my next thing is going to be, so the next thing I would like to do is to actually tell you how to create this these rounds. But before I do this, just something that would be nice if you remember for the following is that this idea of running for f+1 rounds, is gonna come back. It's gonna come back in the partial synchrony setting, right? So in the partial synchrony setting, we will see that we will be rotating. We'll have these views, and we will be rotating the leader between the views, right? So that's idea of rotating the leader for sufficiently many rounds until we hit someone who is correct. Actually comes from this very basic protocol. Okay? Right. Okay. So there are a few exercises here, so they're not intended to be solved now, so just in your free time. So if you really want to understand this model and the algorithms, kind of get into the thick of it, if you want, you can look at how you can improve the message complexity, because message complexity of this algorithm is very bad, right? It's something like n square. So n square messages in every round, because everyone sends message to everyone, and there is f+1 rounds. So this is big O of n square f, and f normally depends on n. So this is essentially cubic. And then you can also say that the number of values that you send n values, so this can be multiplied by n again. So it's quite substantial. It can be improved quite easily. So I would encourage you to think about it. So time complexity is f+1 rounds. I mentioned before that this is a lower bound. Okay, so there is an execution of the algorithm that would run for f+1 rounds. So this execution is the one where adversary kills one node in every round. So as regards to latency, it is possible to design what is called early stopping algorithm. So for early stopping algorithm, I redefine f and t. So now when I say f, I mean the number of processes that actually failed in the execution. And this is the threshold of failure. So it's a maximum that can fail. Okay. So f is less or equal than t. Okay. So it is actually possible to design an algorithm that depends on the number of actual failures in the execution in terms of its latency. Okay, and this algorithm is actually optimal, and the technique for designing it actually quite similar to Paxos if you look at it. But we will talk about Paxos. Maybe then you can consider this exercise. That would be clear. Yeah. So this is optimal latency. So that was proved in particular. There was a nice paper by Sergio and Edith Hidar where they showed very elegant proof that this is the necessary condition. Okay, So switching the gears again. So now I want to see how we can actually construct this round framework from synchrony assumptions. Okay, because this is something. This is already we are moving towards the techniques that we're going to use in partial synchrony. Okay, so here's this very nice round structure that we discussed, right? I can easily build a consensus algorithm in this structure. Everything is nice, but the real system does not have rounds. Okay, so how can we take the basics, right? Basic assumption about synchrony and then convert them to these actual rounds. Okay, so that's the next topic. So what are the synchrony assumptions that people normally make? Okay, so this is upper bound on message delay, delta. Okay, so it's a point-to-point link latency. So it's the upper bound for a message to get from one process to another process. Okay. Then there is another parameter, which is phi. Sorry, we are in the Greek-speaking country. I should say phi, right? Phi. Okay. So if you hear me saying phi, please tell me off. Okay. So phi is upper bound on a relative process speed. Okay. So this is so essentially what is nice about this model is that okay, so just two parameters, we can describe all possible reasonable synchrony assumptions. So so this delta I hope is relatively clear to everyone, but this phi is kind of a bit tricky. Okay, so what do I mean really by that? So the definition says that every phi units of real time, every process takes at least one step. Okay. So essentially what I'm doing here, I'm relativizing time. Okay, time is relative, right? We know that. There is no such thing as absolute time. So what I'm doing here is saying that there is one fastest process in the system, and I am relativizing everyone relative to this process, the rate at which everyone advances relative to this process. So this is how it is defined in this paper. But there is a simpler way to think about it. So kind of we can simplify things a little bit, and then essentially that does not affect the usability of the results. So we can say that essentially we can, instead of arguing about the process steps, things like that, we can think about, okay, every processor has a clock, right? So the clock of a processor, how processor measures time, essentially counts the steps, right? So instead of counting the steps, we can just consider the clock rates. That's it. Okay. So the fastest clock in this model progresses at rate 1, and the slowest clock in this model progresses at the rate 1 over phi. Okay. So that's the model. So we then we can also assume that local processing is instantaneous. So DLS does not assume that, and because of that, they end up with very intricate, very technical argument for no good reason, essentially. But if we make this assumption, the thing becomes much nicer. Okay. So if you're familiar with the clock synchronization literature, then you can probably saw this picture. So this is a real time, and this is a clock rate, a local clock rate. Okay. So this assumption means that there is a so the fastest the clock can advance has how you call this? A tangent? What's the name for it? So this has rate 1, okay? And the slowest would have rate incline, okay? 1 over f, something like this. So this is 1, and this is 1 over f, over phi, okay? And that means that at all times, all processes' clocks are somewhere within this envelope, okay? Right, so that means that clocks actually diverge, right? Unless we do something about that to synchronize them, so this is what happens, right? So even in a system that is synchronous, if we have phi greater than 1, then clocks are gonna diverge, right? So that means that to produce these rounds, we actually need to work, right? It's not for granted, even in a synchronous system. Any questions about that? Okay. Okay, so now I'm starting to design my principal framework, okay? So I would like to design a round synchronizer that has this interface new round, and then on top of this new round interface sits a round-based algorithm, okay? Of course, it is a distributed system, so what we have is that we have a network with delta and phi, right? And there is a synchronizer layer at every process talking to the network using send and receive. And then based on the logic of the synchronizer and what happens, then they can produce this new round indications that these algorithms will use in order to run, for example, round-based consensus. Okay, so let's design round synchronizer. So this, yes, okay, so this is the fundamental requirement that rounds must overlap in time by at least delta. So why it is at least delta? Because we want, so what should happen within the round? So all messages sent from every node must arrive before the end of the round, okay? And that takes at most delta, so processes need to overlap in every round by at least delta. So this is the goal of this round synchronizer. Okay, so question to you. So assume phi equals 1. How can I build a round synchronizer now? Mm-hmm. Yeah, but I insist that I want to design this. So how can I do this? I wait for delta, yeah? Yep. So in each round, I essentially use my local clock, and I know that everyone has the clock that advances at the same rate. Just wait for delta, okay? When that expires, I just produce a new rounds notification. Okay.
Slightly cheating. You're assuming everyone starts in the same.
Yes, I'm assuming everyone. Yes, very, very, very good observation. So we will remove this assumption when we gonna talk about partial synchrony. So for a synchronous system, we're gonna assume that everyone starts at the same time. Because if they don't start at the same time, there is you can think about it as a lack of synchrony to some extent, right? Because everyone sleeps for some random time and then it starts, right? So you can imagine that during the time it slept, their rounds deviated already, right? So you need to do something in order to synchronize them initially, right? So there is a complication here, of course, yeah, but I'm gonna assume this for now, okay? But we're gonna complicate it, don't worry, okay? So now we're gonna have a more complicated, okay, so this is just make sure everyone on the same page. So initially round is 0, start timer for delta, then upon timer expiration, right? So I have this event here, increment the round, start timer for another delta, and trigger new round. Okay, very simple. Okay. Okay. So I actually didn't want that to. I wanted to ask you a question, but okay, let's see. Okay, so pretend you don't see this here. Okay, for now. So now I want to generalize this synchronizer for any phi greater or equal 1. Okay, so now I want to allow for diverging clocks. That's actually okay. Let us just do this quickly. Okay, so how I can do this? So one important observation here is that to time out for x units of real time, a process must set the timer for phi times x, right? So this is important thing to understand. So everyone is okay with that? So yeah, so that should be clear because the clocks. So if everyone sets the timer for phi times x, right, then the fastest process would indeed wait for phi times x, but the slowest would wait for how long? Yeah. Right. X. Okay, so this is the way to ensure that this is the way to implement a timeout. Okay, so so this gives me already a way to deal with that. So I can say in the first round I can set timeout for phi times delta. That would guarantee that the process do not prematurely leave round 0. Okay. Okay, so I have a full synchronized round for round 0, but that's not enough, right? Because after that, if I do nothing, then they again diverge, right? As we have seen in this in the picture, right? Okay. Yeah.
Does the receiver of messages is he able to distinguish messages from round 0 or round 1?
We can essentially that's not a problem. So we can tag every message with the round number. We can. So I'm not talking about it's not to complicate the picture, but of course you need to have a layer that would filter out messages to ensure that the messages from old rounds don't arrive, or messages for future rounds are buffered until this round occurs, right? Okay, so that should be there, but we are not. Let's not complicate. Okay, so this would synchronize in round 0, but then okay, the clocks would diverge in future rounds. So what can be done is that we can now send a message. Okay, so let's call this message sync upon the timer expiration. And essentially, the process who will send this message first is the fastest process, right? And getting this message would wake up all other processes and cause them to catch up, right? So the fastest process would say account would wait enough, right? And understand that the round is over, so now it can also cause others to join it. Okay, so this is the approach. Okay, so this protocol does exactly that, right? So we have initially start timer for phi times timeout. Upon timer expiration, we are not advancing to the next round straight away, but instead we broadcast sync message for the next round. Okay. When I get a sync message for a round which is greater than mine, I would cancel my timer, adopt this round, and then I start a timer for phi times timeout. Okay, and trigger new round notification. Okay, so this this algorithm is smarter than the one we had before, right? So we already advancing towards dealing with this divergence. Yep.
Before there was an exercise which said the square message complexity is very bad, and here we like introduce this.
Yes. Square message complexity is bad. You can improve it. Okay. There are ways to improve it, but I want to show you the principles, and that's the easiest way to do this is with square message complexity. Okay. Right. So let's analyze quickly this protocol. So what we want to do now? So what's the goal of my analysis now is to understand what this timeout should be in order to ensure that delta overlap in the rounds. Okay. So how I can analyze that? Okay. So this is what happens in this system. Let's say we consider a specific round. So this process is the fastest. It notifies these two processes to switch to the next round. Okay. So and they switch to the next round at different times. So the overlap is this green area. Okay. So notice that in this green area, everyone is all the processes are in the same round. Okay. So now we need to compute the size of this green area, or the edge, length of the edge of this green area. So how can I do this? So first observation is that at the time elapsing between the first process entering the round and before it leaves the round is at least timeout, right? This is just because I use this computation here. Okay, so this one is at least timeout. And then there is this yellow area. So what is the length of the area of this yellow area? Exactly. Okay. So this is delta. So it's at most delta. Okay. So we have at least timeout at most delta. So that means that this one is at least timeout minus delta. Okay. So now in order to produce correct rounds, means that I need to initialize my synchronizer with timeout to delta, right? So that would ensure that I have overlap of delta in every round. Okay? Any questions? Okay, this does not work. Why? What?
Sync message also requires the
Yeah, but I took this into account, right? In my analysis, right? So this yellow area is exactly bounded by delta. Why this doesn't work? No. Think about process failures.
Fastest process can crash.
Exactly. Fastest process can crash. And this we have seen from the round-based protocol, if a process crashes, and its message may not get to everyone. Okay? Okay, so so if the fastest process crash in the middle of transmission, then no one else, it's actually the bad situation occurs when some guys get this message and others not, right? So they would advance to the next round while others are not advancing, right? So as a result, we lose this nice picture that we can now bound the overlap. Okay. How can I deal with this situation?
Can we wait for f+1 so that
Exactly. Okay, so we can. So instead of advancing to the round straight away, right? After receiving the first sync message, I will wait. I will wait until I have f+1 messages. Okay, so if I wait until I have f+1 messages, that means that there is at least one process that did not fail, right? That notified me of sync, right? So from that, I can conclude that this process will also tell everyone else that now it's time to advance, okay? So this way I achieve synchronization, okay? Okay, right? So this technique of rebroadcasting, also sometimes known as echo, and it's also the same technique as we will see is used in Byzantine setting, okay? With some modifications, okay? Byzantine settings, we need to increase from 1 to f+1 and from f+1 to 2f+1, etc., right? Okay, but other than that, the same idea works in Byzantine setting as well. So even if I, in theory, don't get to the point that we discussed the Byzantine synchronizer, I already can tell you that you essentially know what it is. Anyway, here's the protocol. I did not debug it, but it should be correct, I believe. Well, at least to sufficient extent. So initialization is the same. Timer expiration, I broadcast a message. Now I receive a message, right, for round R. Check if it is greater than my local round. And then I do this rebroadcasting step, okay, echo step, okay? So notice that I don't, this is the rebroadcasting, okay? So notice that I don't proceed to the next round straight away. Okay, so I first do this broadcast and then I wait. For how long I wait? I wait until I get f+1 copies. Okay. Yeah.
All the process will think they are the fastest. So they will all broadcast.
They broadcasted the timer expiration. Okay. So we wait until timer expires and then they broadcast, right? But fastest would broadcast. Everyone gets its. So for example, if fastest is correct, it will broadcast. Everyone gets its sync message, and they will also broadcast, right? So everyone converges. Yeah.
Fault-tolerant model, f+1.
In which model? Sorry, I don't hear.
In crash model.
In crash model.
Is f+1 really necessary because if the process doesn't?
No, it is not. It is not necessary. You're completely correct. Yes, it's possible to change this protocol, so you actually can tolerate any number of failures. But I intentionally wanted to keep it like this because this is going to be the basis for the Byzantine protocol. Okay. So next slide, there is an exercise that says that asks you to design a protocol that tolerates any number of failures in crash failure model. And it is actually based. You can design something based on a fault-tolerant clock synchronization paper by Dolev, Halpern, and yeah, it's a very good observation. Yeah.
Why cannot any process think that it is the fastest? Because some actually fastest process sent a message, but it is not yet received by other processes. So they think that they are also the fastest ones, and send their own.
It doesn't matter if it is fastest or not. We discussed fastest because it was convenient to talk about the fastest when we did not talk about failures. But what could happen that there's the fastest process and then the other one which lags a little bit behind, And then when it wakes up, its message actually overtakes the message by the fastest that could happen. It does not affect anything in the protocol. Okay. So now, though, we have to modify the analysis a little bit because now it takes 2 delta instead of 1 delta to propagate this thing, right? So the analysis is so before that the overlap is timeout minus delta. Sorry, timeout is overlap is timeout minus the maximum time it takes to propagate the sync message. Okay, so in the previous case it was delta, so now it takes 2 delta because there are in the worst case, right? So for that reason, we need to set timeout to 3 delta. Okay, so 3 delta minus 2 delta is delta, so okay, so we are all good. Okay. So for that to work, we need to assume that the number of failures is at most half, right? Otherwise, we won't be able to. We're not assured to get f+1 things. Okay, so the resilience is not as good as the resilience for the for what can be achieved in a synchronous system. But as was noted, it's actually possible to improve resilience for this protocol. So we keep this f less than n. Okay, and this technique is actually closely related to fault-tolerant clock synchronization. So there was a paper by Lamport and 82, Lamport and Meller-Smith that came up pretty much the same technique, and then that was later improved in this paper by Dolev, Halper, and other people, don't remember their names. So it is possible to do this, but as I have said, we're gonna reuse the same technique for partial synchrony. And the partial synchrony, we still have n over 2f, so it's not really pays off to have something with better resilience because that's requirement still needed for consensus. So that's so for that reason we can just stick to this simple synchronizer. Okay, so I'm wondering if we should let's see. Do you have any questions? Because it's a good time to go for lunch. If you yeah.
Minor one. So with the timeouts, it's true that you're gonna be wasteful. That could be 2 delta plus delta v instead of 3 delta v, right?
Can you repeat?
Timeouts.
Yeah.
In the analysis, you said
Yeah.
timer for 3 delta.
Yeah.
But you could do 2 delta plus delta v, right?
2 delta plus delta phi. Yes. Yeah. Probably. But I need to look at the analysis if that still works. More questions? So if there are no questions, maybe I'll just introduce a partial synchrony model, and then we can have lunch. Okay, so let's talk about partial synchrony model. So partial synchrony assumptions are, okay, so we have delta, we have phi, everything we're already familiar with, okay, it's a completely known territory. Okay, so what is unknown territory? Is that both these bounds, delta and phi, only hold after some unknown global stabilization time. Okay, so that's the that's the partial synchrony. Okay, so so that means that any process, any algorithm that we design for this model needs to be able to cope with arbitrarily long periods of asynchrony, right? So that's, as I kind of showed this graphically, this is some crazy things going on initially, and then there is a global stabilization time, and then everything calms down. Okay, to some extent, right? So at least we know that there are some constants here that that hold, delta and phi, right? Right, and that goes on to infinity. Okay, so you can ask, okay, so why infinity? Is it practical? So it says it's practical, but it goes to infinity. Why that? Why this is the case? The answer to that is that this global stabilization time is unknown. Okay, so processes don't have any local knowledge when the stabilization occurs, so they essentially need to assume, right? At least for safety, this is how these algorithms are designed, that we are still during the asynchronous period, right? So that means that if I have something more practical, so what would be more practical? So something more practical would be like asynchrony, synchrony, asynchrony, synchrony, okay? So if I have something like that, in reality, then the same algorithm is just gonna work as is. Why? Because it's gonna be correct during the synchronous period. Then when there is a synchronous period, if it is long enough, then it will terminate, right? Because we require the algorithm to achieve termination after global stabilization time. And I don't know when global stabilization time occurs, so I need to do my best effort to terminate, okay? So this is why this is a very good model. Okay, so it's understood by both practitioners and theoreticians, and large number of interesting algorithms have been invented for this model. Okay, so let's stop for lunch and we continue afterwards.